In this video, we're going to review some of the basic integration rules that you should have seen from your Calculus 1 course. If not, you may want to look back through Chapter 4 of Calculus 1 and Chapter 5 of Calculus 1. All of these rules are familiar. It's just knowing when to apply which one that is the problem. So I always say that you want to think of yourself as an algebraic sculptor. You need to take your particular equation that you have and make it fit one of these rules. And you can see what they look like here. All of these are in the kind of chain rule U substitution format, so they're very general and you may have to do a little bit of work to get it in the form that you need. So with this first one, I'm trying to find the integral of 9 divided by x squared plus 16. So what I want to do is I want to look at this format and say, okay, what can I let my u be in order to fit one of these forms? And remember that u always has to contain the variable in the integral. So since I have an x as my variable, I know that u is going to have some sort of x in it. Now I'm looking through this, and a lot of students try at first with the integral of du over u, or u prime over u. You might see that one written that way. But in this case, if I tried to let u be x squared plus 16, I would run into a problem because my u prime would have to contain a 2x, and we don't have the x we need on top. So we can't make that format work. We're going to have to do something a little bit different. So I'm scanning down the list, and I notice that I've got the x squared plus 16 here. I notice that number 19, the arctangent, has the integral of du over a squared plus u squared. So I think this one might work for me. And if I let u be equal to x and I let a be equal to 4, so that a squared could be equal to 16, I bring the 9 out front. Of course, u prime here would be 1, so du would be 1 dx. And then I'm just going to switch the x squared plus 16 to be 16 plus x squared. Then making the appropriate substitutions, what I now have is 9 times the integral of du over a squared plus u squared. Now we can see that that evaluates to be 9 times 1 over a times the arctangent of u over a plus c. The 9 doesn't have to get multiplied by plus c. You just consider that as plus c to be a constant. And then now I just have to fill in my a and my u. So I'll have 9 times 1 over 4 times the arctangent of x over 4, all plus c, or 9/4 times the arctangent of x over 4 plus c. And that would be my final answer. Now notice the only difference between parts A and B is that A has no x in the numerator, whereas B has an x in the numerator. So in this case, I actually want to let u be the x squared plus 16, because if I let u prime be 2x, du, which is u prime dx, would be 2x dx. I have all the variables that I need in order to make the rule that says the integral of du over u equals the natural log of the absolute value of u plus c work. So what I'm going to start with is I'm going to bring the 9 out front, and I will have 9 times the integral of x over x squared plus 16. And let's just go ahead and pop that dx up into the numerator so that everything works out nicely. I need a 2 here in order to complete du, and since I multiplied by a 2, that means somewhere I've got to divide by a 2. So I'm going to do that on the outside. And remember, we can do that as long as we're not multiplying by the variable of integration. Anything else you can multiply on the outside with, but just not the variable. So now that I've done that, I have 9/2 times the integral of du over u. And according to the list, that evaluates to be 9/2 times the natural log of the absolute value of u plus c, which is 9/2 times the natural log of the absolute value of x squared plus 16, all plus c. Now it's fine to leave it like that, but if you observe that x squared plus 16 is always positive anyway, so we don't really need that absolute value symbol, we could remove that and just have the natural log of x squared plus 16 times 9/2 plus c. Either one would be accepted as correct. So you can see what one little tiny x, it makes a huge difference in how you evaluate your integral. So keep that in mind. You may have to try a couple of different rules first before you find the one that fits your problem. But don't give up, because it will be on that list somewhere. Now this next one is still very similar, but it has an x squared instead of an x. So I noticed that the degree of the numerator and the denominator are the same. So just glancing through my list of rules, I don't see anything that accounts for that, because obviously if your u has an x squared, your u prime is going to have an x. It's not going to have an x squared. So what I want to do when I see something like this is I first want to try long division. So I'm going to take the long division, I'm going to divide 9x squared plus 0x plus 0 by x squared plus 0x plus 16. So when I do that, I will say 9x squared divided by x squared, which gives me 9. So I'll place that here. I'll multiply back through. And 9 times 16 is 144. I will change the sign by multiplying by a -1 on this row. And everything will go away except for the -144. So this expression right here is equivalent to 9 minus 144 over x squared plus 16. So I can integrate that instead. And of course, the first thing I want to do is break it into two integrals. So I'll have the integral of 9 dx minus the integral of 144 over x squared plus 16 dx. I'm going to I can go ahead and actually evaluate this. This is 9x. That one's pretty easy. I'm going to bring the 144 out and have the integral of 1 over x squared plus 16 dx. And we actually already looked at this one. If we let u be equal to x and we let a be equal to 4, du would be u prime dx, which is just dx. So this is minus 144 times the integral of du over a squared plus u squared, if you swap the order there, which you can because it's addition. So I'll have 9x minus 144 times the integral of this guy, which evaluates to be 1 over a arctangent of u over a, and that's all plus c. And a is 4, so we'll have 1 over 4. We'll have the arctangent of x over 4. And canceling what cancels, 144 and 4 simplify to be 36. Of course, you can't touch this x over 4. It just has to stay like it is. So my answer for this one is 9x minus 36 times the arctangent of x over 4, all plus c. So you could see, scrolling back through these, one little power of x changes things dramatically. And in C, we needed to use some algebra before we could actually integrate. Now, you may find a lot of your integrals require more than one basic rule. And here's an example of this one. I've got the integral from 0 to 1, so this is a definite integral, of x plus 2 divided by the square root of 9 minus x squared, all with respect to x. So with this one, I've got a square root of a number minus x squared. So I'm kind of looking at this rule right here and thinking number 18 is probably where I'm going to be. But notice that on top, we need to have du for whatever the u is. So with this one, I think that I can use the number, but the x could be a little bit problematic. So what I'm going to try doing is I'm going to split this up into two integrals. I'll have the integral from 0 to 1 of x over the square root of 9 minus x squared dx. And I'll have the integral from 0 to 1 of 2 over the square root of 9 minus x squared dx. So this is like two separate problems side by side. On the left here, I noticed that if I were to let my u be 9 minus x squared, u prime would be negative 2x, and du would be negative 2x dx. I do have the x that I need, I just don't have the negative 2. So I'm going to multiply by a negative 2 here, and a negative 1/2 here to cancel it out. So that'll allow me to write this as negative 1/2 times the integral from x equals 0 to x equals 1 of 1 over the square root of u du, or the integral from x equals 0 to x equals 1 of u to the negative 1/2 du. So we'll deal with that one in a second. Now, we used a u here. I'm going to call this u1 just so we don't get too confused because we don't want to have a different u on either side and be using the same variable. Now with this one, I can't use u equals 9 minus x squared because I don't have an x on top. So what I'm going to have to do is I'm going to have to use the integral of du over the square root of a squared minus u squared. So I'm going to let my a be 3, and I'm going to let what we'll call u2 be x. So du2 is going to be u2 prime dx, which will just be dx. So I'm going to bring the 2 out front, and I'll have 2 times the integral of x equals 0 to x equals 1, and that'll be du over the square root of a squared minus u squared. And we haven't actually integrated anything yet, so I'm just going to go ahead and bring this down one more line. Now the reason why I'm keeping these x equals 0 and x equals 1 instead of just writing the number is that I'm trying to remind myself that, hey, these are x boundaries, these are not u boundaries. So we want to be a little bit careful with that because we don't want to mix up which variable goes where. Now you can convert bounds straight away by plugging in 0 and 1 into whatever your u is for the problem, but I just like to do it at the end. It's my personal preference. Okay, so I'm going to evaluate this one on the left, and I've got u sub 1 to the negative 1/2. So we're going to add 1 to that. That's the power rule. And that's going to go from x equals 0 to x equals 1. On this side, because we have du over the square root of a squared plus u squared, we're going to use that rule 18 from the list, and that's going to be arc sine of u over a. And this is u2, so we're going to go from x equals 0 to x equals 1. Now here, I'm going to have negative 1/2, I'm going to have u to the positive 1/2, and then I'm going to have a positive 1/2 here. So that's going to cancel and just leave a negative. And u to the 1/2 is a square root, so this is really the negative square root of u1, which was 9 minus x squared. And that's going to go from 0 to 1. Over here, we're going to have 2 times the arc sine of u over a, so u is x, and a is, in this case, 3. And again, I'm just going to try and do all this in one step. So I'll evaluate this definite integral using the fundamental theorem of calculus. I'll take the square root of 9 minus 1 squared, that's a negative on the outside, and subtract the negative square root of 9 minus 0 squared. And then here I'll have 2 arc sine of 1/3 minus 2 arc sine of 0 over 3. So this gives me negative square root of 9 minus 1 is 8, plus the square root of 9 minus 0 is 9, plus 2 arc sine of 1/3. 1/3 does not have a, it doesn't have a clear, pretty exact form for the arc sine, so we're just going to leave it as it is. We're not going to actually evaluate that. But the arc sine of 0 is actually equal to 0. And I'm going to reduce this radical, so 8 equals 2 times 2 times 2, so the square root of 8 is 2 square root of 2. The square root of 9 is 3. So just carrying that over, we get negative 2 square root of 2 plus 3 plus 2 arcsine of 1/3. And that is my final answer. Remember, we want exact forms. We do not want decimal approximations unless you are instructed to round. So if it doesn't tell you to round, plug in the actual, or put in the actual exact value as your answer, and this would be considered the exact value. Next, we're going to look at the integral from 0 to 1 of 2x minus 4 divided by x squared plus 4. So in this case, I'm going to split it up into two separate integrals again. So I'll have 2x over x squared plus 4 minus the integral from 0 to 1 of 4 over x squared plus 4. And this is, of course, with respect to x. On this side, if I let u be x squared plus 4, u prime would be 2x. So du is 2x dx. So we have the integral from 0 to 1, and that's x equals 0 to x equals 1, of u prime over u dx. On this side, I'm going to use, we'll call this one u1, u1, so on and so forth. On this side, I'm going to have a 4 over x squared plus 4, so I can't use the same u, but what I can do is let a be 2 and let u be x. So if I bring the 4 out front, what I end up with is the integral from x equals 0 to x equals 1 of du over a squared plus u squared. So that's our friend arc tangent. So here, the u prime over u gives me the natural log of the absolute value of u from x equals 0 to x equals 1. And here, we're going to have 4 times 1 over u, so that'll be 1 over u, I'm sorry, 1 over a, not u, 1 over a, times the arctangent of u over a plus c, and that's u2. This is an a. u1 was x squared plus 4, and really you don't need the absolute values here because x squared plus 4 is positive, but we'll leave it as it is. A is 2, so we end up with 4 halves times the arctangent of x over 2, all plus c. Well, actually, we don't need a plus c. We have a definite integral. This goes from x equals 0 to x equals 1. So I'm going to have the natural log of 1 squared plus 4 minus the natural log of 0 squared plus 4. I'll have 2. We'll have the arctangent of 1/2 minus the arctangent of 0 halves. So here I can reduce these radicals. This will be the natural log of 5 minus the natural log of 4. Neither one of them have a nice pretty decimal answer. And here we'll have the arctangent of 1/2 minus 0 because the arctangent of 0 is 0. So I'll collapse these logarithms just to clean this up a little bit. And of course the 0 is going to go away. So I end up with the natural log of 5/4 minus 2 times the arctangent of 1/2. Neither one of these have nice, clean, exact values, so we're just going to leave them as they are.